Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. Thank you very much. I'm Philip Emeagwali. To invent is to see something that was previously unseen and to see something that did not previously exist. I invented new computational mathematics that are important to my oil-producing country of birth, Nigeria, and that will enable the petroleum industry to use the massively parallel processing supercomputer to discover and recover otherwise undiscoverable and unrecoverable oil and gas. I invented new computational mathematics because I asked important mathematical questions that are central to the toughest problems in computational physics. The research pure mathematician asks questions that are directly centered on mathematical knowledge itself. I am the research massively parallel processing computational mathematical physicist who asked mathematical questions that had corresponding physical answers. As a pure mathematician of the 1970s, I knew there are no easy quote-unquote new mathematics. Also, I knew that it is beyond the intellectual reach of somebody trained only in pure mathematics to possess a deep understanding of the 81 partial derivatives that represent the four physical forces that define the second law of motion of physics, and to as well understand that 36 partial derivative terms are missing in the mathematical physics textbooks on the multi-phase porous media flows, and missing since Darcy's law was empirically discovered in 1856, and missing since Darcy's formula was used in lieu of the 9 Emeagwali's partial differential equations of modern calculus. That lack of deep knowledge of physics was the reason a pure mathematician could not discover and correct the mathematical errors that I discovered in the central partial differential equations of the physics of the petroleum industry, and could not invent the new calculus, the new algebra, and the new algorithms that I invented in the early 1980s, and that were the cover stories of top mathematics publications, such as the cover story of the May 1990 issue of the Siam News. The Siam News is the top publication in mathematics. The Siam News is written by research mathematicians and written for research mathematicians. I was not on the cover of the top mathematics publications because I was good looking. I was on the cover of the top mathematics publications because I contributed to mathematics. Why is the word algebra the recurring decimal in school reports about the contributions of Philip Emeagwali to mathematics? The reason algebra is my recurring decimal across school reports and across my ensemble of 65,536 processors is that I invented partial difference algebraic equations, and that I use those algebraic equations to approximate the 9 abstract continuous partial differential equations of modern calculus that I also invented. Those Emeagwali's equations in turn encoded the second law of motion of physics that were discovered 3 centuries earlier. In the finite difference discretization of the continuous initial boundary value problem of mathematical physics, extreme scale algebra is the recurring decimal. Extreme scaled algebraic computations were executed by the massively parallel processing supercomputer that computed the weather forecast in your evening television news. Algebra is about using the known to know the unknown. Today's weather forecast, that is a known quantity, is used to forecast tomorrow's weather, that is an unknown quantity. For that reason, algebra, which is used to know the unknown from the known, must be used to know tomorrow's weather from the known weather of today. So every television viewer that is watching this weather forecast is a secondary consumer of the algebraic knowledge that was massively parallel processed across the modern supercomputer. Before my experimental discovery that occurred at 10:15 a.m. New York time of Tuesday, the 4th of July of 1989, only one processor within an ensemble of 65,536 processors could be harnessed to solve the toughest initial boundary value problems in computational physics and computational mathematics. That singular processor was de facto merely a computer. After my experimental discovery of the 4th of July of 1989 of how all those 65,536 processors could be harnessed and used to solve the toughest problems, that global network of processors that was also a new internet was de facto a new supercomputer. That experimental discovery is the reason the name Philip Emeagwali came up first when Google was queried with the search phrase, "Contributions to the development of the computer." At the granite core of my experimental discovery was how and why I emailed 65,536 initial boundary value problems, and why I emailed them with a one-to-one correspondence to 65,536 processors. Each email I sent and received from each processor contained data and answers for and from the Emeagwali new system of equations of algebra that I had to solve. The Emeagwali new system of equations arose from my system of coupled, nonlinear, and time-dependent partial differential equations of a new calculus that I encoded in the early 1980s into a set of laws of physics. The Emeagwali's new system of partial differential equations contained the most advanced and the most important expressions in modern calculus. The Emeagwali's new system of partial differential equations is mathematically equivalent to the system of partial differential equations that were used to define one of the 7 millennium problems of mathematics. The slight difference between the Emeagwali's new system of partial differential equations and the system used to define the millennium problem was in the real-world domain of the initial boundary value problem that was governed by the system of partial differential equations. The Emeagwali's new system of partial differential equations governs the subterranean motions of fluids such as oil, water, and gas that flow underneath the surface of the earth. The millennium equations govern the motions of fluids that flow across the surface of the earth, such as rivers, lakes, and oceans, and govern the motions of fluids that flow above the surface of the earth, such as the wind and moisture that condenses to rain and snow. The initial boundary value problems that I experimentally discovered how they could be solved were called grand challenge problems for a good reason. I experimentally discovered how to solve the toughest problems in extreme scale computational physics and solve them across a new internet that is an ensemble of commodity off-the-shelf processors that are identical to each other and that are equal distances afar and apart from each other. That project was a massively parallel processing supercomputer research that should have been conducted by a large multidisciplinary team or conducted by a lone wolf parallel processing supercomputer scientist who is both a jack of several sciences and a master of several sciences. To succeed in experimentally discovering the new massively parallel processing supercomputer was like looking God in the face. The lone wolf supercomputer scientist must be a polymath instead of a mathematician. The reason the grand challenge problem was impossible for a mathematician that was trained only as a mathematician to solve is that that mathematician could only think on his blackboard. The polymath visualizes the grand challenge solution to the grand challenge problem and visualizes the time to solution across boards and visualizes that time to solution from the storyboard to the blackboard to the motherboard and finally across motherboards. I, Philip Emeagwali, used my multidisciplinary knowledge that I acquired over 2 decades of specialized training that spanned from geology to meteorology, from calculus to algebra, from computer to internet. And I used that multidisciplinary training to conceive and to execute the crucial supercomputer experiments that led to my experimental discovery on the 4th of July of 1989 of how to massively parallel process across a new internet. That's a global network of 64 binary thousand commodity off-the-shelf processors that are identical to each other and that are equal distances afar and apart from each other. Back in the 1970s and 80s, almost every vector processing supercomputer scientist believed that parallel processing is a huge waste of everybody's time. So I was executing my massively parallel processing experiments and executing them against the orders of the leaders of thought in the world of computing, such as the Steve Jobs of personal computing, and against the opinions of the leaders of thought in supercomputing, such as Gene Amdahl and Seymour Cray. In the 1970s and 80s, the terra incognita that was the emerging field of massively parallel processing, supercomputing, was as empty as a ghost town that had only one permanent resident. I, Philip Emeagwali, was that permanent resident of the farthest frontier of supercomputing called massively parallel processing. In the 1970s and 80s, if you could find your way to any massively parallel processing supercomputer, its administrator will deem you worthy and grant you a supercomputer account to become its lone wolf programmer. Because the internet of the early 1980s was then uncrowded, I had an unusual email address from the early 1980s. That email address had no .com suffix. In the mid-1980s, I had the email address spelled Emeagwali @.com. Emeagwali was spelled like my last name without the last letter I. Think.com was the second registered .com suffix. That global network of 64 binary thousand commodity off-the-shelf processors that I experimentally discovered that it could be programmed to solve the toughest problems in computational physics was a new internet. That new internet was a small copy of a never-before understood internet that had only 65,536 processors around a globe instead of billions of computers around a globe. I visualized each of my 2 to the power 16 commodity processors as equal distances afar and apart from each other and around a globe in a 16-dimensional hyperspace. And I visualized my ensemble of processors as evenly distributed across the hypersurface of a hypersphere in a 16-dimensional universe. I visualized my ensemble of processors as outlining a new internet that I visualized in my 16-dimensional universe. I, Philip Emeagwali, was the David from the world of the massively parallel processing supercomputer that was ridiculed and mocked for challenging the Goliath named Seymour Cray, who designed 7 intense supercomputers in the world of the vector processing supercomputer of the 1970s and 80s. I visualized my massively parallel processing supercomputer as my slingshot that is a small copy of the internet that can shoot 65,536 small pebbles from its as many processors. Those pebbles were my metaphors for the as many initial boundary value problems of modern calculus and computational physics. I visualized shooting all the 65,536 small pebbles at once. I can only record the fastest computations and record them across 65,536 processors and record them by throwing all my rocks at once instead of throwing them one at a time. In the 1970s and 80s, I was the David of supercomputing. I was ridiculed and caricatured by well-regarded supercomputer scientists. I was called a lunatic and dismissed from research teams that believed that all supercomputers must do only one thing at a time. Seymour Cray, the Goliath of supercomputing, believed that all supercomputers should compute only one thing at a time. Seymour Cray was armed with one big sword. Seymour Cray's sword was my metaphor for his vector processing supercomputer. Seymour Cray's most famous quote is this, quote, "If you were plowing a field, which would you rather use, 2 strong oxen or 1,024 chickens?" Unquote. As reported in the June 20, 1990 issue of the Wall Street Journal, I, Philip Emeagwali, experimentally discovered that 65,536 chickens that learned to work together or work in parallel can plow more field than the strongest ox that walks alone. I'm Philip Emeagwali. I am the subject of school reports because I invented a new supercomputer that was the precursor to the modern supercomputer. I invented a new supercomputer that is a small copy of a new internet. The new internet that I invented is defined and outlined by an ensemble of 65,536 commodity off-the-shelf processors that are identical to each other and that are equal distances afar and apart from each other. That new internet is complex, abstract, and a mystery. The 65,536 processors of my new internet were married together by 1,048,536 576 bidirectional email wires and married together as a new supercomputer and computed cohesively, and did so as one new integrated supercomputer and computed seamlessly as one new internet. My 64 binary thousand processors that outlined my new internet communicated via emails and did so with a complexity that I cannot completely describe in words alone. Nor can I completely describe my processor-to-processor email exchanges and completely describe them as equations on a blackboard alone, or completely describe them as algorithms on a motherboard alone. I began supercomputing at age 19 on June 20, 1974 in Corvallis, Oregon, United States. I was the lone wolf and the only full-time programmer of the fastest supercomputer of the 1980s. Today, the fastest supercomputer cost the budget of a small nation. The fastest supercomputer is programmed by thousands of supercomputer scientists. The fastest supercomputer occupies the space of a soccer field. The holy grail of the fastest possible supercomputer is to marry together all the processors in the world and marry them to all the computers in the world and marry them to all the supercomputers in the world and marry processors and computers and supercomputers together, and as a never before seen internet that will become a never before seen planetary sized supercomputer that will turn our science fiction to our descendants' non-fiction. I'm Philip Emeagwali. I am the massively parallel processing supercomputer scientist that conducted research alone. I am the massively parallel processing supercomputer scientist that conducted research alone and conducted it from the age of 19 in Corvallis, Oregon, United States, to the age of 35 in Los Alamos, New Mexico, United States. To the supercomputer scientist, Los Alamos, New Mexico is the capital of supercomputing. Prior to my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July of 1989, it was said that parallel processing is a beautiful theory that lacked experimental confirmation. Prior to the 4th of July of 1989, I was the unknown supercomputer scientist who told his massively parallel processing supercomputer story alone and told it to no supercomputer scientist in particular. In fact, my 1,057-page report that I distributed to vector processing supercomputer scientists of the 1980s and that described my new supercomputer was at first thrown into the trash. After my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July of 1989, I became a known supercomputer scientist, and those that threw my 1,057-page report into the trash wanted to become my new best friend and clamored to retell the story of how I experimentally discovered the massively parallel processing supercomputer that is a new internet. As I became more known, I discovered that many insidious voices were clamoring to retell my story and to retell it in their visions rather than in my original vision. I discovered that there are 1,000 secondary voices can drown my primary voice. I discovered that the story of my new supercomputer, that is not a computer per se, but that is a new internet de facto, was reduced to a cacophony of secondary voices. I want to redeem my story and reclaim my voice and make my voice the loudest voice in the world of the modern supercomputer, and make my voice to be continuously heard, to be the most continuously heard voice in the history of the internet. Each of my processor within my ensemble of 65,536 processors had its unique name, that's also its unique email address, that's 16 bits long. I used a binary reflected code to generate my 64 binary 1,000 unique names that were each a unique string of 16 zeros and ones. With the binary reflected internet naming scheme that I used, if two email addresses differ by only 1 bit, then the processors that corresponded to those two email addresses differ by only 1 bit. And those two processors were directly connected. That connection allows nearest neighbor email communications that maximizes the speed I could attain while executing my floating point arithmetical operations. My 64 binary 1,000 emails traveled across 1 binary million or 1,048,576 bidirectional email wires. I had theorized that speed increase of a factor of 64 binary 1,000, and therefore I was expecting to experimentally discover the world's fastest speed in computation. Even though I was expecting the world's fastest speed in computation in 1989, I was shocked and in disbelief when the world's fastest speed in computation popped up on the computer monitor of my 4-brained workstation that front-ended my 64 binary 1,000-brained massively parallel processing machine. Even though my experimental discovery matched my companion theoretical discovery that preceded it a decade earlier, I developed an imposter syndrome. I developed it in part because I was black and African. I developed an imposter syndrome because I was ostracized and only one white computational scientist attended the first lecture of massively parallel processing that I gave in November 1982 in Washington, D.C. Because I developed an imposter syndrome, I convinced myself that I made a mistake. Due to self-doubt, I wasted half a year, the last half of 1989, searching for the mistake in my new massively parallel processing supercomputer code that did not exist. My eureka moment felt like a jolt of electricity. I screamed loud for others to hear. Ewo! 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 I screamed in my ancestral Igbo language of Onitsha, Anambra, the former East Central state of Nigeria, West Africa. On the 4th of July of 1989, I experimentally recorded a world record computational speed of 20,000 calculations per second. Then my screaming continued for half a year, with each small increment that led to a new world record. My computational speed peaked at 47,303 calculations per second for each processor that I massively parallel processed through. My supercomputer speed that made the news headlines in 1989 was achieved in a high-level programming language. I discovered that my new massively parallel processing supercomputer could compute 4 times faster if I had computed with a low-level programming language that could have enabled me to use an assembly-coded routine and use it to reduce the execution time of my most computation-intensive kernels. The supercomputing world record that I recorded in high-level programming language and recorded in 1989 totaled 3.1 billion calculations per second across my parallel processing machine that was my new internet. That fastest computation was recorded across a new internet that's a global network of 65,536 processors that's de facto a massively parallel processing supercomputer. The eternal quest of humanity for faster computing aids that began with the abacus in ancient China remains the holy grail of computing. Yet, that quest had only one paradigm shift. I paradigm shifted from computing within only one computer that was powered by only one processor to supercomputing across a new internet that is a global network of 64 binary thousand processors, or supercomputing across a global network of as many computers, or supercomputing across a new internet that computes by massively parallel processing. In the 1970s and 80s, the grand challenge of communicating across that new internet was ridiculed and mocked as follows: parallel processing, or supercomputing many things at once instead of computing only one thing at a time, is a beautiful theory that lacks an experimental confirmation. The June 20, 1990 issue of the Wall Street Journal mentioned that I, Philip Emeagwali, experimentally discovered how to massively parallel process and how to simulate the multi-phase subterranean motions of oil, water, and natural gas flowing a mile deep inside an oil field, and how to simulate the production reservoir by dividing the oil field into 65,536 equal parts that I emailed to 65,536 processors. That experimental discovery was also the cover story of the May 1990 issue of the Siam News, the flagship publication of record of the research mathematics community that was published by the Society for Industrial and Applied Mathematics, and that was written by research mathematicians and written for research mathematicians. My first newsworthy speed-up result that occurred on the 4th of July of 1989 was a quantum leap in supercomputer performance. It was either a zero speed-up or a 65,536-fold speed-up. There was no speed-up between 0 and 64 binary thousand. I recorded a 65,536-fold increase in both the speeds of email communication and arithmetical computation. I experimentally discovered the fastest supercomputer when I experimentally discovered the fastest supercomputations and discovered them across my hyper-global network of 65,536 processors. My networked processors, or as many computers around a hyperglobe with 1,048,576 bidirectional email wires. A world record speed in arithmetical computation and email communication. A world record speed in arithmetical computation and email communication puts a man and his machine inside the terra incognita that is the magic zone of the supercomputer and the new internet. It hits the sole programmer of all those 65,536 processors as a jolt of electricity. Right away, my few confidants said I will be famous. The paradigm-shifting technology, named the massively parallel processing supercomputer, that I experimentally discovered, changed the way we do the most computation-intensive arithmetic on the modern supercomputer. The supercomputing paradigm shifted away from executing floating-point arithmetical operations that arose from extreme-scale algebra and shifted away from executing those operations in the singular. The supercomputing paradigm shifted to dividing the computation-intensive initial boundary value problem into 65,536 subsets of arithmetical problems that were equal to each other and that were equal in terms of total floating-point arithmetical operations count, and sending those 65,536 email messages that each contained a subset of arithmetical problems, and following each email with floating point arithmetical computations that solves the companion initial boundary value problem, and most importantly, executing the computation and the communication in the plural senses. I realized the profound and the paradigm-shifting meaning of that never-before recorded 65,536-fold increase in speed. A grand challenge problem that took 65,536 days or 180 years to solve will now take only 1 day to solve. That experimental discovery opened the door to today's world of massively parallel processing supercomputing, in which a grand challenge problem that takes 30,000 years to solve on one processor will now take only 1 day to solve across 10,649,600 commodity off-the-shelf processors that is at the core of a massively parallel processing supercomputer. For those still enmeshed in the old paradigm of sequential computing, their 30,000 years of sequential computer work is merely 1 day in my new paradigm of massively parallel supercomputing. I discovered the paradigm in which the boundary between the computer and the internet is blurred. When I began supercomputing on June 20, 1974, I envisioned a planet-sized global network of computers that was the precursor to the internet. In subsequent years, I invented a new internet that I called a hyperball that was described in the book titled History of the Internet. I also invented a second new internet that I called a cosmic ball. In the mid-1970s, my new internets remained science fiction. But on the 4th of July of 1989, I constructively reduced that hyperbole science fiction to non-fiction. And I did so when I became the first person to experimentally discover that an ensemble of the slowest 65,536 processors in the world can be harnessed to compute faster than the world's fastest supercomputer, and do so while solving the toughest problems in extreme scale computational physics. At its logical core, my technological quest to record the fastest speed in supercomputing and to record it across a new internet, that was my ensemble of 65,536 commodity processors, was indirectly a quest to find the elusive email communication path and to know the unknown communication primitive that was a quest to find the communication path from each commodity processor to its 16 nearest neighboring commodity processors. My email communication breakthrough occurred when I discovered a new paradigm in email communication, namely how to use a new addressing scheme that was counterintuitive but self-relative. In the old paradigm of computing, supercomputer scientists used an addressing scheme that was intuitive and absolute. With my self-relative addressing scheme, I repeated the email messages that I sent to and received from my 2 to the power 16 commodity processors. With my mathematical discovery of the self-relative addressing scheme, my self-doubt evaporated like dew in the sun. After that mathematical discovery, my confidence soared, and I started seeing myself as the first massively parallel processing supercomputer scientist that could experimentally discover how to make the impossible to compute possible to compute. To the 25,000 vector processing supercomputer scientists of the 1980s, that lacked my new knowledge of self-relative addressing scheme. Philip Emeagwali seemed like a lunatic that was pursuing the elusive goal of massively parallel processing across an ensemble of commodity processors that was a global network of 65,536 commodity processors. That was a new internet. I invented a precise minimalist code with email communication primitives that belies its power. My code was so minimalist that my email messages to and from 16-bit long addresses appeared invincible. I wanted my data to be transported from each vertex of the hypercube. That was my metaphor for a commodity processor to its 16 nearest neighboring vertices that had a one-to-one correspondence with 16 nearest neighboring commodity processors. I visualized my emails as flowing quietly and seamlessly across the surface of a hypersphere that was embedded in a 16-dimensional universe, and doing so with the accuracy a cat deploys to tiptoe deftly through a laid dinner table. I, Philip Emeagwali, experimentally discovered how to email 64 binary thousand challenging initial boundary value problems of modern calculus and extreme scale computational physics, and how to email them to 64 binary thousand processors. I, Philip Emeagwali, experimentally discovered that those ensembles of processors define and outline a new internet that I visualized as my small copy or blueprint or prototype of the internet. I sent each of my primitive email to a 16-bit address or a unique string of 16 zeros and ones. Each email address had no @ or .com suffix. Each email contained 5 sets of data. I visualized each email as having 5 subject lines. I visualized each emailed processor code as a computation-intensive initial boundary value problem in modern calculus or extreme scale computational physics that I sent to each of my 2^16 processors. I visualized each emailed code as sent along 16 times 2^16 bidirectional edges of the cube in the 16th dimension that had a one-to-one correspondence with as many email wires that I visualized as short wires printed onto circuit boards or as long wires comprised of fiber optic cables. I visualized each email as sent with no message body. I visualized around a globe in a 16-dimensional in the 16th dimension because my problems and their data or email messages were contained in 3 subject lines were received by 65,536 processors that I visualized as uniformly distributed around a globe in a 16-dimensional hyperspace. After each email was received, the 2 subject email lines that contained the sending and the receiving 16-bit long email addresses become useless. I discarded those 2 email addresses after each email was received. I visualized my new internet as outlined by 65,536 commodities that were identical to each other and that were equidistant from each other. Each processor was like a dim light in a sea of darkness. But when supercomputing together as one seamless, cohesive supercomputer, those 65,536 processors became as bright as the sun. I communicated around my new internet, that is a global network of 65,536 processors, and I did so by email, and I did so before each set of arithmetical computations, and I did so by imagining myself as 65,536 travelers in hyperspace. As an aside, any global network of commodity processors that are identical to each other and that are equal distances afar and apart from each other can be flattened from 3 or 16 dimensions onto a two-dimensional motherboard. Topologically, and to the supercomputer scientist or mathematician, that 16-dimensional network of commodity processors still remains a global network of processors. That global network is electronically soldered onto a two-dimensional surface. That global network on a two-dimensional motherboard is not renamed a two-dimensional network. To rename that 16-dimensional network as a two-dimensional network will be akin to renaming a 16-dimensional hypercube that was drawn on paper as a square, or akin to renaming a 16-dimensional hypersphere that was printed on paper as a circle. Put differently, I had one neural human brain enhanced by 65,536 electronic brains. My email travel paths were along communication email wires that encircled the surface of a globe in hyperspace that I visualized as short wires printed onto circuit boards or as long wires comprised of fiber optic cables. My destinations were my equidistant processors that I visualized as distributed on the surface of that hypersphere. I imagined myself, Philip Emeagwali, traveling into higher and higher dimensional universes. The farthest I could travel was to and from 2 to the power 64 equidistant processors. A new internet connected those processors and connected them with 64 times 2 to the power 64 identical email wires that I visualized as short wires printed onto circuit boards or as long wires comprised of fiber optic cables. In the 64th dimensional universe, I had an eureka moment. I discovered it will be presumptuous of our children's children to imagine they could construct a hyperbole that will talk in the 64th dimension to think 2 to the power 64 times faster. I was in the news headlines as a result of my experimental discovery of the massively parallel processing supercomputer. That experimental discovery occurred on the 4th of July of 1989. I was in the news headlines because I brought a new face, a new voice, and a new vision to the story of the development of the modern supercomputer. that is not a computer per se, but that is a new internet de facto. That experimental discovery of the massively parallel processing supercomputer that is the precursor to the modern supercomputer came from both intellect and intuition. For me, Philip Emeagwali, that precursor to the modern supercomputer, is the coming together of my 35-year life experience, life journey and experiences. Prior to my experimental discovery, the use of the massively parallel processing supercomputer and how to use the technology to solve the toughest problems in extreme scale computational physics was not taught in any university or tested in any laboratory. Nor can the technology be learned. Instead, the new massively parallel processing supercomputer that solves the toughest problems in abstract calculus and extreme scale computational physics and solves them faster than the vector processing supercomputer had to be seen for the first time, and seen on that 4th of July of 1989. By definition, to discover is to see something that was previously unseen. A scientist on a research for new knowledge is a truth seeker, especially new truths. A supercomputer scientist on a research for a faster supercomputer is seeking a new supercomputer, and especially a new computer. The discoverer becomes the first truth seeker. The scientific researcher is on his or her hero's quest for the previously unseen truth. Our never-ending quest for the fastest possible supercomputer has become our journey to the frontier of human knowledge. That never-ending quest has become a self-directed evolution in which we are both the creator and the created. That journey to the end of knowledge will force our post-human descendants of year million to address the larger question of who we are and where do we want to go. Daalụnụ, afam bụ Chukwura Philip Emeagwali, abụ m onye Ọnịcha. Bịa ga-afụ m na emeagwali.com ka o mesịa. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you. Thank you. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.